So this is the inclined plane with friction assessment. So the situation we have is we've got a inclined plane, coincidentally, and a block, and there is friction on this block. But what we do with this block is we give it a shove up the ramp, and it will move up the ramp and then back down. What we need to do is draw a force diagram for the block when it is on its way up the ramp. So we know first, one more thing, this angle is 53.1 degrees and our block is 5 kilograms. Okay, that's cool. The forces on this block, we have the earth pulling it down, and that's going to be equal to the mass of the block times the gravitational field strength of the earth. So that's going to be 5 kilograms times 10 newtons per kilogram, which will be 50 newtons. We also have the normal force that's going perpendicular to our surface. We don't know how much that's going to be yet, but we'll figure it out. We also have friction on the block, which is going the same direction. Since our block's going up, the friction is going to be pulling it back. So we have friction right here. Don't know how much it is. And then we also have, these are like the secret forces. We have the component forces of our mg. One that's going to be parallel to our normal force, and another one that's going to be parallel to our frictional force. And these two, we also know that this angle is going to be the same as this angle. So that's going to be theta right there. I'll just call it theta instead of saying 53.1 each time. We know that this side is going to be mg sine theta, because it's the opposite from the theta, and this one's going to be mg cosine theta. So that's awesome. So now we got all our forces described. What we got to do is compare the acceleration of the block going up the ramp and the acceleration of the block going down the ramp. So we know that when the block's going up the ramp, it's accelerating down because it's slowing down, and eventually it's going to turn around and come back down the ramp. So we know our acceleration up the ramp, well, acceleration always equals F net over mass. That's just a given. This situation, our F net is going to be our friction force, because our normal force, it's not accelerating anywhere that way. So this force, the normal force on our mg cosine, is going to cancel out. So that's no net force there. But we do know that this mg sine theta, which is the x component of our mg, and our frictional force are going to be the net forces on the block. So we got F plus mg sine theta. Divided by our mass, 5 kilograms. So that's going up. So that's when it's going up. When it's going down, you get a whole different one. When it's going down, we're still having the mg sine theta, and the mg cosine theta is balancing out the normal force, which I need to label. So we got mg sine theta, but the friction, when the block's traveling down, the friction's going the other way. So our force, our net force, is actually going to be mg sine theta minus the frictional force over 5 kilograms. So we, just looking at this, we know that going down, the acceleration has to be less. It has to, because this quantity is going to be less than this quantity. That's just the raw fact. And so because the F net going up the ramp is bigger, the acceleration going up the ramp is bigger. Alright, so we got that. Next thing we want to do is so we're given the coefficient of kinetic friction between the block and the ramp is 0.2 newtons per newton. Okay. What they're telling us here is that mu, our symbol we use for the coefficient of friction, is going to be equal to F over N, and they're just telling us that the whole situation is going to be 0.2 newtons is equal to that. So that's cool. And we want to calculate the acceleration of the block on the way up the ramp. So we already have our acceleration formula, which we can transpose down the board. Acceleration equals F plus mg sine over mass, which is just 5 kilograms. So since I've talked about this a few times before, but since we have no acceleration in the y direction, this normal force and our mg cosine theta has to be equal. So our normal force, let me just write that down as our little factoid. Normal force is equal to mg cosine theta. Okay. We have that. And if we rearrange our mu equation, because what we're trying to figure out here is F. If we rearrange this guy, we can set it up where F is equal to N times 0.2. And we just figured out that N is equal to mg cosine theta. So now this equation, we can figure out the friction. So we got to rewrite this with our new information. We know that F is going to be N times 0.2. And we know that N is mg cosine theta. So we'll write it out as 0.2 times mg cosine theta plus the mg sine theta all over our 5 kilograms. So this is kind of complicated, but we've now set it up so the only thing we need to plug in is mg, which we know to be 50 in both situations, and theta, which we know to be 53.1. So after plugging in all that stuff, do all the work, you get acceleration equals 9.2 meters per second squared. Awesome. So that's great. The next thing we need to do is they tell us that the critical angle is 22 degrees. So, and the critical angle they define for us is the angle to which you can raise the ramp until the block just slides. So I gotta erase some things in order to do more math here. So our critical angle, which you can write as theta c, is 22 degrees. Okay. Calculate the coefficient of static friction. So they're talking about this. Calculate that at the critical angle. Oh wait, no, not at the critical angle. If we know the critical angle, we're going to be able to figure out the coefficient of static friction between the block and the ramp. So we know this is 22 degrees. And since we know that at the critical angle, all the forces are just balanced, just perfectly balanced, that our friction is going to be equal to our mg sine theta, because our net force in the x direction, because our net force in the x direction is 0. And we know that the net force in the x direction is mg sine theta minus f. You can set that equal to 0, and we get mg sine theta equals f. So wow, that's cool. And our net force in the y direction is also 0 because it's not moving, right? So we get n is equal to, oh, hold on. Our net force in the y direction is going to be mg cosine theta minus n. This equals 0. So n must equal mg cosine theta. Since we know those two things, and since we know mu equals f over n, mu now equals mg sine theta over mg cosine theta. So this is big. We can cancel out our mg's. And we're now left with mu equals sine theta over cosine theta, which is just tangent theta. So we can use our angle for theta and just plug in tan of 22, and we get 0.4, which means mu will be equal to 0.4 newtons of frictional force per newton of normal force.